Let's see here. Okay, I think we should be good for the live now. Okay, so welcome back once again to another AP Calculus free response run through here. Let me go ahead and make sure this is all up to date. So we are dealing with the 2018 packet now. So welcome everyone once again to the 2018 AP Calculus free response run through. So as many might know beforehand, though, that all questions are welcome through the chat. We'll be able to answer that through immediately, or again, anything sent to the email, the one that's right there on the left side, the labcodemath@gmail.com, will be also an acceptable way to get your questions in if you have any at all. Of course, be sure to slap that like button for us to be pushed through the algorithm. But nonetheless, though, we'll be going through all of the problems. There will be 6 of them on this AP Calculus exam, and all of the questions and answers will be written down on the notebook. So you can either review this at a later time, as all of the recordings will be put through our VOD system, or you can go and follow along right now if you wish as well. Okay. So I think that should about do it. Again, just as a quick reminder, we go through 2 problems at a time before we go over the answers, and I do grade myself out of all 54 points that are usually assigned to the free response section of this exam. And we'll get to see how well I hold up with all the things that I have been teaching on my channel to see if anything will match with what we have. So without further ado, why don't we go ahead and start this process, and we will see what happens going through this. So that does remind me, though, for our first 2 problems, very quickly, we have ourselves our graphing calculator. So I'm using my trusty TI-83, the old tried and true calculus calculator that can definitely handle all of the integrations and graphing that we need for the first 2 problems, and the last 4 will not need one anymore. So we'll keep this off to the side. I'll show what my calculations look like as well as we go through each problem. So why don't we go ahead and get through problem number 1, and we'll see how this goes along. So I will go ahead and start putting this down. We'll copy it through and we'll take a look. And here's here that people enter a line for an escalator at a rate modeled by the function r given by. So now it'll give us a lovely function for us. It's a piecewise function, so we have 2 parts to it. We have the first part of 44 multiplied by all of t over 100 raised to the 3rd power of 1 minus t over 300, all raised to the 7th power. And the rule here is that it's for our interval going from 0 to 300 for t. And lastly, a nice easy 0 when we have the rule for t being greater than 300. Okay, so with that rule, we can then see it says here that this is where r of t is measured in people per second, and t is measured in seconds. As people get on the escalator, they exit the line at a constant rate of 0.7 person per second. Quite odd to have a decimal person, but that's just the way averages work here. And also there are 20 people in line at t is equal to 0. Okay, very nice. So with that, we can go ahead and start getting to actually problem number 1, or part A for this problem. It says here that they're asking how many people enter the line for the escalator during the time interval from 0 to 300. Alright, there you go. Our very first part of this problem that is being shown right now. So, if they're asking for how many people enter the line, again, that's asking for a flat number of people. Right now, all we have is just the actual rate. So, again, R of t is the people per second that enter the line. So, we have a rate instead as the function of R of t, and we do not have the actual number of people. So we need to take a step back, again reverting back from the seconds per seconds down to just the number of people in between time 0 to 300. Again, they want to know how many people enter. They don't exactly care for how many people there were, like that 20 people at the start. That is not important to this problem. So in order to go backwards from a rate to the actual net number of people that enter between the two time zones here, is that we will then have to take an integral going from 0 to 300 for R of t in respect to time, so dt. And so we do some very simple substitution on this. So we go from 0 to 300 for the entire function of 44 times t over 100, all raised to the third power, multiplied by 1 minus t over 300, all raised to the 7th power dt. Okay. Now this is something that is very easily able to be inputted into our calculator into a simple answer, and that should be part A for this problem. So what we have here is that we have our trusty calculator. Let's clear that out. So I can go ahead and start inputting. So with my integral function on the calculator, we can then start putting everything through. So it'll be 44 multiplied by all of, let's see, we can use t in this case, so t over 100, that is. Okay, all raised to the third power. Okay, and so with that, we can continue by multiplying it now by 1 minus all of t, t over 300 now. So all of that now instead, in that parentheses, will be raised to the 7th power. And then this will be for our variable t, going from 0 to 300. Okay, so that's what it will look like on our calculator right there for the entire function. Separating the variable t, that's the one we're integrating from 0 to 300. Okay, so by slapping that through our calculator, we get an answer of 270, a nice even answer here. Okay, so that is 270 people will then enter the line. Okay, that is part A of the problem complete. Let's move on to part B. Okay, so part B says here that during let's see, the time interval from 0 to t to 300, there are always people in line for the escalator. How many people are in line at time is equal to t being 300. We don't need that first equal sign. Okay, so that says here that there are always people in the line in the escalator. So how many people are in line at the time of 300? Okay, so once more, this is where we're going to have to go ahead and use our good old friend, the fundamental theorem of calculus, because we already know from 0 to 300 for that rate that we've already solved for. But according to the fundamental theorem of calculus, so I'll abbreviate that as FTC, that'll mean we have the people on the line, so I'll use capital P for that. So the people at time 300 in the line subtracted by people in the line of time 0. Again, that is the definition of our integral. And thankfully, because we already know exactly what the integral is, because we calculated that in part A, and they already gave us the p of 0, which they gave us as the 20 people in the line. Okay, and so then we can see how many people are in the line at exactly the time of 300. So with some simple substitution here and some adding of variables here, we have that 270 people that was from the integral. We add the 20 to it for the people that were there at the very start of the line. Okay, and so from there we have the actual number of people all at the time of 300 being at the 290 people in line. Okay, and there you have it. So we have that, but that actually is going to be, right, again, that's the people that entered into the line. Okay, so that's one thing that we do have to keep track of, that isn't exactly the answer, because now we need to see how many people have left that line, right, which they do give us as that 0.7 people per second is that constant rate of people leaving that line. So because this is just a standard 300 seconds that pass of that many people leaving, all we need to do is multiply that by 300, and then we then get the by adding a 0, that's that should be 210 people that have left the line. So a very simple subtraction of 290 enter minus the 210 leaving will give us an easy 80 people in line at the 300 second mark that they are referring to at the start of the problem. Okay, and that should be very simple for us to follow along with logically, because once again, to go over it, right, the integral means that this is how many people that just came into the line, right, during the entire time frame from 0 to 300 seconds, while we still need to keep track of the amount of people that have left the line because they're getting onto an escalator, so the line will thin out. And the problem already told us that it's 0.7 people per second that leave that line. So just by multiplying that 300 seconds for how long it has been since we're checking back, that means 210 people must have left that line. So all that's left are just 80 people in line in that escalator. Okay, good. So with that, we can get to problem C here. It says here that for t being greater than 300, what is the first time t that there are no people in line for the escalator? Okay, so now that we're getting over 300 in terms of seconds again, so remember that r of t is equal to 0 if t was greater than 300. So again, this also means that no more people are entering the line. Okay, so again, no one else is coming into line, so all we have is just that 0.7 people per second leaving, right? Okay, but then of course we still have that exactly from part B, the 80 people left in the escalator. All right, so to calculate the amount of time it takes, right, that there are 0 people left and that all the people on the line have been taken care of, we just need to do a very simple division problem. There's 80 people being divided by the 0.7 the people per second. That would mean just how much time it takes for all of that to be emptied out and that many people to be back onto the escalator and no longer in line. Okay, so a very simple division problem. This one could take the use of a calculator for those who wouldn't want to waste the time on that, since it's a calculator section. So because that gives us a lovely decimal answer, we can just round it off, I think, to still still 3. I just prefer to do the standard 3 if it's in decimals, just so that the test creators will know that we're trying to be as accurate as we can. So 286 seconds. Okay, that's how long it takes for 80 people to leave the escalator. So now we need to add that onto the 300 seconds. Again, because we started at 300 seconds, this is where we started recording that. And then we just need to add the 114.286 seconds. So that total will give us 414.286. Where did that 8 come from? It's 286. Okay. And that's kind of messy, so let's try one more time. So 414.286 seconds is the time for escalator line to be empty. Okay. There you go. So that will be part C for that, showing about where the escalator line will be empty after no more people are coming into that line and only people are exiting to get onto the escalator. Okay, part D and the last part for problem 1. It says here for 0 going between t to 300. Okay. At what time t is the number of people in line and minimum. Okay. It says here to the nearest whole number. Find the number of people in line at this time. Okay. And so we need to then find that time of t where the number of people is going to be a minimum. Thankfully though, because we already know that the number of people that enter the line, okay, so p of t again being the people entering line, okay, we can then go ahead and see about what that number will look like for this graph, meaning that we need to look at the r of t graph. Okay, and it's only from the 0 to 300, and because r of t already is the derivative of p of t, again in terms of that people per second that are entering into that line. So let's see what that looks like on our graph here. So let's go ahead and see to it that we plug it in. So 44 times all of, this time I have to swap it to x because we're on a graph, all raised to the third power, multiplied by 1 minus the x, make sure we put that in parentheses, so the x again over 300, so all of that raised to the 7th power. Okay, so again we have, I don't like the look of that, oh no, that's fine, that's correct, yeah, because all of that 1 minus is all raised to the 7th power, and then x over 100 raised to the 3rd power. So make sure that we put into our window that our x is going to go all the way to 300, because that is the limit to which we will have that, and we just are looking for when we get a cross on that axis. So we're going up and down, and then we kind of stand still there. Okay. Alright, so because of that, yeah, there doesn't seem like there should be, and yeah, there really shouldn't be any negatives here to begin with. So with that rate being there, we need to then see what the minimum will look like. So I wonder if we have something here. There's people in the line at minimum. So that's that. I wonder if we have something that, pretty sure if we were able to graph that integral, but I doubt they're going to want us to do that. It's because it's continuous, so because the starting people, it starts at 20 and then at the end of 3 seconds is 80, so you basically do a little bit of a climb up to that. But that also means that because we have that 0.7 here, Let's see, I wonder if subtracting 0.7 people per second is going to help clear. Oh, that's going to be in the same line here. Okay, so minus the 0.7. I don't know if that might change the way we start on. Okay, there we go. Because we're at the constant rate of people leaving, and we dip under again, and we go underneath the rest of the way. Okay, so there we go. We have some of our possibles here. One being, of course, the minimum being that lowest point right there. Okay, and of course our starting points as possible absolute minimums as well. So let's go ahead and find where that 0 is here. So let's go and move all the way back here. Okay, so make sure we are in the negative for the left side of that 0, and then make sure we go above it to go on the right side. And we will end up with a 0 at, it says here, the 33.013. Okay, but now they wanted to nearest whole number. It's a number of people, so the time is actually going to be in 3 decimal places. So 013. Okay, so the t at 33.013 seconds. Again, that's a local minimum. And again, we have 0 and 300 to also keep track of as well for some of the absolute minimum candidates to see if we are actually at the lowest point. So at 0, what he told us is 20 people. And then at 300, that's already 80 people. Okay. So all that means that we need to find that integral for the 33.013 seconds, and we'll try to see how many people are there. So because of the fact that R of t is just the people entering, we need to keep track of the people that are leaving. So again, that's R of t minus 0.7. And we take that integral from 0 to 33, oh yeah, it shows 0.013 seconds in respect to time. Okay, so that should be fairly easy enough for us to put into our graph, our integral here. So let's see. So we have our integral from prior on that subject right there. We're just going to change that limit instead to 33.013. Okay, but also we need to then see if we can insert in the subtraction of 0.7, because that needs to be implemented in there as the people that are leaving and keeping track of that integrated across the time frame that we are looking for. Okay, that ends up as a negative 16. I think that makes sense because that will be the subtraction of the 2. Let's double check that just to be sure, because then that's going to be, that negative is equal to, yeah, that should be fine because that's the R of 33.013 minus R of 0. So we just need to add R of 0 to both sides. So that's going to be the plus 20 to both sides. So R of 33.013 is going to be adding a 20 to the nearest. That's 4. Yeah, that's 4 people still left. And so that is indeed the smallest number that we do get for the for that line of the escalator. So again, we have the 33.013 seconds. That's going to be the lowest time and the lowest amount of people, thanks to the integral and using our good friend fundamental theorem of calculus to understand that. So as a quick overview, again, we were looking back at that graph. So again, we had the graph. In this case, again, we're keeping track of the minus 0.7. That's also a rate that could be subtracted from R of t. So again, it's entering minus leaving. So with that, we do have a nice graph, which we can easily find where that cross from the negative to the the crossing from the negative to the positive side for this graph, meaning that it's going to be a relative minimum. So at that time is going to be that 33.013 seconds that was stated for this function there. And so by running the fundamental theorem, again, it's the people entering minus the people leaving at the 33.013 seconds, we do get a result of that. Let me show that again. That was going to be the negative 16.1, if we rounded it. So that's the result of the integral. Load is a negative number. You might be thinking, well, what does that mean? Again, this is the amount of people that have left that line since, because it's a negative number, since that 33 seconds. But of course, because there were already 20 people to begin with in that line, that just means that we have 4 people remaining in that line at the time being until we get back to that 0 eventually after the 300 seconds. So with that, we found exactly what they wanted to. We'll come back to this once we are through the problem number 2, and we'll correct both 1 and 2 once we get through that. Alright, very good. So let's go over to problem number 2, and we'll see what they want on that side. So to copy it down here, it says here on problem number 2, let's see, a particle moves along the x-axis with velocity given by the function v of t is equal to 10 multiplied by the sine of 0.4 t squared all over t squared minus t plus 3, okay, for the time going from 0 to t to 3.5. Okay, it says here as well that the particle is at position x is equal to -5 at time of t is equal to 0. Okay, there you go. So we have a whole section here of the particle moving along the axis here. So the first question though is asking us to find the acceleration of the particle at the time is equal to 3. Okay, so that is our first problem that they are asking for us to do. Okay, so which means that we just need to find a velocity taking that derivative. Remember that relationship of v of t, take that derivative in respect to time, will give you the acceleration graph. So because of that, we want to find the acceleration at 3 instead. So this is something that is easily done from the calculator point of view, in that with our math button here, I can go down and to the function derivative, where at least my calculator, it can't give me the result of a numerical value so long as we plug in a number for the variable that is in question in that function. So because of that, let's go ahead and plug in the velocity function already. That's going to be all of the 10 multiplied by sine of 0.4. This time it's going to be t raised to the second power. Okay, and then because of that, we can divide it all by the variable t squared minus t plus 3. Okay, so all of that will then be taken in account for the variable of t at the value of 3 that we're looking for. Okay, so it seems like they didn't like what I put in there. So let's see here. We have the function is not closed properly, so let's insert in one more parentheses. That should do it. There you go. Okay. Oh, parentheses issues, of course, a classic amongst calculators. But nonetheless, though, we do get a number here from exactly what we plugged in. And that looks about right for this, if we were to take the derivative, with this being good old quotient rule with a lot of subtraction going on for now. Okay, so negative 2.118 is going to be the right rounding for that, so let's keep that in mind. So negative 2.118. Again, there are no units, unfortunately, for this, so we're just going to leave it as such, as an acceleration result from a function there. Okay, and it says here next is to find the position of the particle at the time t is equal to 3. Okay, very good. A position question, which means, of course, we will then need to integrate the velocity in respect to time using good old fundamental theorem once more. But this time they did give us an initial position. Remember that the initial function of x of 0, so at time of 0, that position is -5, something that they pointed out at the beginning of the problem here. So, because of that, if we took the integral going from 0, now we want to end it at 3, because that's what they're asking for, of that velocity function in respect to time, fundamental theorem would very easily tell us that the position at 3 will be found, as well as the difference between that and the position of 0, meaning that the position of 3 is just going to be the position of 0 in terms of the time added to the integral going from 0 to 3 for the entire velocity function of 10 times sine of 0.4 t to the second power all over t squared minus t plus 3. Okay, in respect to time in that integral. Okay, so all of this can be very easily plugged into our calculators here, and we shall see what this turns into. Again, t at x of 0 being -5 for this. Okay, so with that, we can get our calculator set up right here. So once more, we will want to go back to keep track of that -5 first on the outside being added to now. We will then go ahead and tell the calculator we want to do an integral of the 10 times sine of 0.4 times t raised to the second power. I'll make sure it's raised to the second power properly, like that. Okay, so all of this needs to close once for the sine, once for the numerator. Then we go into the denominator of t raised to the second power minus all of t. Okay, and then plus 3. So there you go. So that closes the denominator, and so we will move on to identifying that it is the variable t we're integrating for from the limits to 0 to 3. Okay. So with that, it can run through and make sure we're all looking good with a -5, 10 times sine, all of 0.4 t squared, then all of that divided by t squared minus just a t plus 3. Okay, -1.760. Okay. -1.760. Thankfully, again, because we took care of that -5, there are no second steps in the calculator. It's all done in one. So we have the answer to part B already. Okay. Once more, the full understanding of how fundamental theorem works, especially for this kind of problem, that when you integrate the velocity amongst two limits, you're going to get the difference between those two limits back a step into the displacement function. And so with some easy algebra and some entering in the calculator, we will get the exact answer that we are looking for. Negatives are fine in terms of position, because that would mean that we are just in the opposite direction of our positive way for that particle. Okay, next it says here in our question to evaluate the integral from 0 to 3.5 v of t dt, okay, and evaluate going from 0 to 3.5 the absolute value v of t dt. Okay, and then it says interpret the meaning of each integral in the context of the problem. Okay, very nice. So we have all of that to look forward to, in the sense that we have both the original velocity function in the integral going from 0 to 3.5, but also we have the absolute value of velocity in the integral going from 0 to 3.5. A very interesting prospect, but something that we should know what that means in that sense. But in any case though, let's first go and just find those numeric answers, and then we will explain our ways through to earning the rest of the points here. Okay, so for each of them, we just have to run them separately on our calculator, and we will then see what those will turn into. Okay, so we already have that v of the velocity one already done. If we go backwards here, as shown right here, if we can focus right there, that again, we already have the entirety of that function, 10 times sine. It's just that we had the limits just going. That is the derivative. That's not what we want. Let's clear that out here. We wanted this one. So the integral just going this time from why does it keep saying derivative? No, we're going back. There we go. The integral. Okay. the integral now. This time it only goes up to the... That is not correct. Where is it? This is getting a little bit frustrating. Where is our one that we did the integral for? Okay. Jeez. Alright. Sorry, this was kind of hard to see, but okay, so we have the one for the integral going from only 0 to 3, and we also had that -5 added in front, thanks to the problem B of adding that -5 there. So we just need to swap it to a 3.5 on the limit, and forget that -5 there from the start, and we should be good in terms of that coming through. Okay, so with that, we're just going to clear out that -5 that we started with. So it's just the integral of that function. But we got to make sure to change that limit. Instead of a whole 3, it's a 3.5 that they asked us to evaluate for. And then we send it right on through. And that gives a positive 2.844 if we round it to the third decimal. So 2.844. Okay, that's the result of that. But then we must be able to go and see that with the previous entry, that we can go ahead and insert in the absolute value for this entire function. So let's see if I can get that to work here. So with an insert, we want to go and put in the absolute value expression there. Boom, right there. And it looks like that's pretty good. Everything is inside of the absolute value where it needs to be. And then make sure we close off the insert in the last parentheses just to make sure everything and our calculator shows that it will be inside of the absolute value for the entire function, and then still evaluate for the value of t going from 0 to 3.5 as normal, and we send that one on through. And this one should be able to be rigorously calculated by our lovely machine here. Pretty sure it just takes a second because we are asking for a lot for it, so let's give it just a moment here. Good. With a 3.737, then we'll be rounded. That does make sense for us, and we'll get to the reasoning in just a moment. Let's write that down, though. 373. 3.737, like there. Okay. So what does that mean for either case in terms of this problem, right? Is that we have just the integral of the velocity being 2.844. Okay, so that's just the difference between the v of 3.5 minus minus x of 0. So there's no difference in terms of the way that we are calculating for that. But in any sense, though, because we have the absolute value, then that would mean that we change all those negative areas back into positive ones, which goes to show you why the velocity 1 in the absolute value does have a larger value than the one without it. Okay, so in terms of just the final minus initial as the way that it is for the first guy, right? So again, the integral from 0 to 3.5 for just v of t dt is the net displacement for the particle. Okay, and the net displacement just means, again, like, where do we start and where do we finish, right? Okay. On the other hand, though, if we were to take into consideration that absolute value of v of t dt, okay, and that is the total distance traveled for the particle. Okay, so that means, again, any sort of backtracking with that velocity, again, so any negative values on that velocity function doesn't matter. We just swap it back up to positives again, because we are just looking at the total distance that was traveled for that particle through the entire section from 0 to 3.5 seconds on the time. Okay, so we'll go ahead and box those answers as ones that were retained from our calculator, and that will be the explanation that we can give for the context of that particle moving across that track. Okay, so lastly, let's go to part D here. It says here that a second particle moves along the x-axis with position given by x sub 2 of t is equal to t squared minus t for going from 0 to t to 3.5. Okay. At what time t are the two particles moving along, moving with the same velocity. Okay, so we have another particle moving along and we want to see if the velocities will ever match. Okay, so what that does mean is that because we have only just the position given for the second particle, if we want to calculate velocity, that just means we need to get the velocity of that second particle quite easily, with the second velocity being equivalent to the second position, taking the derivative respect to time. So because of that, we just move everything down. So it's 2t minus 1, which is that guy. Okay, and so they want to see at a time in which the two particles will have the same velocity. So because of that, we just take this guy again. So if we have them equal to each other, so v of t for the first guy being equal to v of t of the second guy, in terms of that, all we need to do if you want to look at it graphically is do a lovely subtraction problem. And then if it's equal to 0, they are obviously equal to each other if they are subtracted from each other and they enter up as 0. Something very easily seen on a graph. Of course, our time interval is just between 0 to 3.5. So that's something that we want to keep track of because we don't want to go any further than we ever have to for ourselves. So let's go ahead and put that right into our calculators here. Let's make sure we are on the same page about this, because it's going to be the v1 of t, which is going to be 10 multiplied by the sine of 0.4 t to the second power, all divided by t squared minus t plus 3, subtracted by all of 2t minus 1. Again, we want to see if that's equal to 0 on the graph. Okay, so let's go ahead and put that into our calculators here, and we'll see what that looks like. So for this guy, we just need to take all of the 10 times the sine of 0.4 times, now make sure we switch it to x because we are graphing here, x squared, okay, and then divide it all by the x squared minus x plus 3. Okay, so we have all that as the first part of that first particle's velocity. Then we just subtract it with all of the 2x minus 1. So let's make sure we have the 2x minus 1. Okay, and there you have it. We have the two functions there. We just got to make sure we don't want to look at it between -1 and 300. That's way too much. We just need to look at it between 1 and 4, and that should give us a very good segment to look at. If we take a look at how this graph goes, it looks like we touch and we cross over right there. Good. So let's go ahead and find where that 0 lies, and that should be the result of the 2 there. So left bound being if we're above the axis, yeah, we are on that point, and we just go a little bit forward to make sure we're below the axis, and let's have a look at what that looks like. Okay, very good. So we end up with exactly with y being 0 of 1.571 if we round that properly. So the time is equal to 1.571 for when, again, this is exactly where both velocities of the two different particles are exactly the same within that range that they gave us for the particle of t. Okay, of t going between just 0 to 3.5, we have exactly what we need to prove that we are dealing with the exact time where the two velocities are the same as each other, setting them up and running the graph. Okay, so that is all 4 parts of problem number 2. So it looks like we have everything here to begin our first grading part here. Let me make sure I get my right red pen here just to make sure we have it separately there. So again, just for everyone that might be new here, is that we are looking at the 2016 AP Calculus FRQ response questions. So to show what that looks like right now, again, there is the scoring guidelines. All that is posted online for the viewership of anyone else to use. So again, I'll be going over each individual answer and looking to see how well I score points-wise across those different questions. So going back to it, I'll show you again from what we have on our notebook here for all the questions that are answered. We're going to the first two problems that are the calculator sections, and we'll see how well I scored and if any corrections need to be made accordingly. Okay, so because of that, let's go back to problem number 1 here. So this is about the issue with the escalator. So we run that integral. They want us to show us that exactly want to go from 0 to 300 on that escalator. That's exactly what they wanted us to have. So that's 1 point for me already on that. And the answer of 270 people entering that line, that is indeed 2 out of 2 correct for me. On that, that's pretty good to start. Then part B, we end up with, make sure we have that, that difference between just the actual integral, but then keeping track of the fact that we have the 210 people leaving, again because of that rate of 0.7 people leaving. I could have shown they asked for just the consideration of rate of people out, which is exactly what we have here. But if I were to show it in a more cleaner sense, it would have been that we would take the integral, and I showed this in a later portion, just that it would be r of t minus the 0.7 dt. Because again, that 0.7 was that constant rate of people leaving. R of t is the rate of people entering, subtracted by the people leaving. I kind of did that on a separate thing on its own, but in any case though, the 80 people that are left in the line, that's exactly what they're looking for as the answer. So in either case, it's 2 out of 2 still correct for part B. Okay. Then moving on down to part C, it then goes that we have they just care about only the answer. So 414286. Yes, that is exactly the answer that they only cared about. Wow, that's a little bit something. But just as a quick reminder is that they wanted the time at which the escalator line emptied out, because after 300 seconds, there are no more people entering into that line. So it was indeed just a very simple division problem of trying to see how long it took for people to leave, which it took 114 seconds around for all the people to empty out. We just slapped it on top of the 300 seconds that it took for the escalator to stop adding more people, and therefore we get the answer that they were looking for. So part C is a 1 out of 1 correct for us on that. And then lastly, for part D here, we have the total number of people, and we wanted to see a minimum. So we did indeed have the different justifications here. So so going with those considerations, right, that it's going to be, we have that graph set up there, and we do need to identify that 33.013 is indeed the correct timing for which we have a minimum for that. And so with that, we just run the calculation, and we do end up with 4 people being left in the line as that they were asking for. Again, the justification shown in the work here as we show our last bits of things there for our setup and for the different time frames in which we are considering when a minimum would occur at either the endpoints, so when we start and finish on this timing, or also at the local minimum as was shown on the graph that we had for this problem. So all of them are correct, especially with the answer, so that's 4 out of 4 correct on this part. Okay, very nice. So it looks like I got everything correct so far in this first problem. So that is a 9 out of 9 on the entire page. Something I can do here that makes it a lot easier for me to calculate my total is that at the very front of the test packet, I will section off each question down to 6, because there are 6 problems on this whole packet. So Q5 and Q6. Okay, so with that, we can go ahead and put down each points that were given. So 9 out of 9 for that first one, and we'll see how well we score and add them all up, and we can get a percentage out of it. Okay, so let's go over to problem number 2 as corrections, and then we will pick it back up with problems 3 and 4 for us to go over. Okay, so problem number 2 is that we do get the acceleration. We just plug that thing right into the calculator, and all they do care about is just that answer of negative 2.118 was exactly the match here. So again, this was just a very simple plugging right into the calculator because we're just taking the derivative of that velocity function. So that is a 1 out of 1 correct for me on that. Okay. Then for part B, it says here that we are looking for that positioning there. So they do want us to run that integral from 0 to 3 v of t dt. That's exactly what they want to see. Then we have that initial condition of that minus 5. Again, that was part of x of 0 using the fundamental theorem of calculus that we have right there. So again, I'll take a note on that. Again, that's a fundamental theorem of calculus shown as we understand exactly what the definite integral means for us. And so with that, we keep that negative 5 up in front, and we get the answer of negative 1.760. So that does match as well. So that is 3 out of 3 correct for me on that. Okay. Then we will continue with the evaluation here. Is that for part C, we just run both straight through the integral. So 2844 is correct, and the 3737 is also good. And the interpretation is showing that we are looking for just the net displacement over the time without the absolute value. Again, because we just keep track of all the negatives and going across it, getting rid of that from our final calculation. While the absolute value does give us a larger answer because it is going to be that total distance that was traveled by the particle. Again, considering all the negative movements that we have, back is positive as the particle travels even more further from there. Okay, so all that is correct. So that's 3 out of 3 correct for me because of that. And lastly, for part D here, we have the we want to set that. Yep, we have to take that velocity of that second particle they asked, which is going to be the first derivative of the equation that they gave us for the second particle. And so we just set them equal to each other, and then with that we get the answer of time being 1.571 as the rounding. That's also good. So both of them are exactly what they're looking for. So that is 2 out of 2 correct on this part as well. Very good. So without anything missed out on this part, that will be another 9 out of 9 on this portion of the test. Very nice. So let's put that on the front of our packet as we get ready to move on to questions 3 and 4 on the packet here. Okay, so just as a reminder, again, for anyone else that is watching or seeing this through the VOD, is that you can send all of your questions, again, to that right side email there, the labcodemath@gmail.com, or send it straight through the chat, and we'll see if we can answer what is being on the minds of our students here. Okay, but without any further things going on here, we can move on to question number 3. Okay, if our cameras will decide to focus here, because it says here for questions 3 all the way to 6, so the last 4 questions here that we're going to go over, there is no calculator allowed on this, so we'll toss this graphing calculator away to the side for now, as the rest of these problems will not let you use one. Okay, so I think I can have some fun here, graphing out what they have on this problem number 3. Again, if you haven't seen it, there was quite this nice looking graph here. I could do the same by just copying that right down and doing the work all on my notebook here. Okay, so make sure we have everything shown here. There's a height of 8 going up here, so let's make sure we keep track of that. And a -3 on that. Okay, takes up some space, but I think it will be all the better for it. So we go 1, 2, 3, 4, and 5. One more. Okay, and then we need to go 6 across. 1, 2, 3, 4, 5, and 6. We go up to 8. 1, 2, 3, 4, 5, 6. 5, 6. Yep. 7 and 8. And then we go 1, 2, 3 down the bottom. Okay, good. So let's start graphing this. We start at that -3 all the way going to -2. Okay, so let's go right there. Okay, then at -1, there's -2, -1, we shoot right up to the 0 point right there, go across 1, then we shoot up 2 more again here, and then we go straight across to 3. And then we dip down to 4, let this curve there, and then we shoot at 6, 8. 6, 8 all the way up there. So we just go something like that. Okay, kind of crude, but this does match exactly what we're looking for on this graph. Again, they're going to take a note that this is the graph of G for this function. Okay, and which the function g, they note here on this problem, is that the g of x is equal to the first derivative of the different function f. Okay, and then let's see here. So it's linear. Something to note is that linear with -5 of x going to 3 for g of x, and it's going to be the function that now switches to 2x minus 4 all of that squared for the interval going from 3 to 6 on g. Okay, very nice. So that is going to be the context for problem number 3. So let's get into the actual problems itself. So part A says here that if f of 1 is equal to 3, what is the value of f of -5? Okay, so now they want to see what an actual instant value is going to be. So because of that, given that we want f of -5, again, we have that relationship that g of x is equal to f prime of x, right? So in that case, if we want to go back to the original function of x, we're just going to have to go and take the integral of that first derivative of f. But that also means is that we can't just take it because we don't have the actual result of the integrals, but we do have the points here that we want to go from -5 to +1. Okay, both of which are outside that range of the actual graph of the equation form of g. So we'll just have to keep that in mind, as fundamental theorem will very easily show us that we are dealing with the function of 1 back in the normal sense subtracted by f of -5. Okay, so with that difference, again, we will have the actual value for that. So we can go ahead and see what that will look like, because again, this is going to be the actual integral itself, thanks to, once more, fundamental theorem coming to our rescue. This is just the area under the curve. Okay, for the graph of g, because again, they already noted that g is the first derivative of f. Okay, so along with that, we can go ahead and start finding that. Again, going from -5 all the way back there to a +1, which is up there. Okay, which means just for us, we can split this accordingly. I wonder if I can switch to a different color here so that it can be easily seen on this graph here on what we're looking at. Because we have here a nice rectangle and a nice triangle down there, and then a nice triangle up there as well. Okay, so we have those going along for us for the ride in terms of that area going from -5 all the way to +1. Okay, so because of that, we can then start splitting this up and seeing what that area will look like. So just the integral itself, so the first derivative, is now going to be then equal to the areas of those sections there. Okay, so you first have a rectangle going, looks like here 1, 2, 3, 4 across. So first we have a 4 base across, but we have a height of -3 as that rectangle part right there. Then we have then the triangle here, which has a base of 1 and the same height of -3, but also because it's triangle, we need to multiply it by 1/2, keeping in true with all of our geometric equations here. And lastly, we have that last bit of a triangle up there with the base of 1 times the height of 2 with 1/2 because it is a triangle. Okay, so we just need to run this through and we could come up with some areas. So that's -12 for the first guy, and then a -3/2 for the second guy, and then a +1 after that. Okay, we can run a mixed number here just for now because it makes life a little bit easier. So we get a -12 and 1/2 because of that. And with that, that should be just the definite integral itself, but we still need to know what the actual f of -5 is. So to plug everything back into the equation here is that we have f of 1, which is 3, minus the f of -5. All right, that's what we had so far. We want to isolate the f of -5. So by moving things over in terms of the integral here, it will be 3 plus the 12.5, which will be 15.5 waiting for us. in the result of all of that. So that point is going to be 15.5. Again, in terms of a improper fraction, if that's what they want on the exam, 31/2 will be the result for that point after all of our work, thanks to the fundamental theorem of calculus. Okay. So just as a quick recap on that, for those I know that fundamental theorem might be a bit of a problem for some students, is that they've already defined that g of x is the first derivative of f. And so if we want to find the original function of f, we just need to take the integral of that first derivative. But we also need limits to help us to reduce them back to singular points, which is what fundamental theorem asks for us to do in the first place. So we can set our points, 1 being our answer, our target of f of -5, and the one of f of 1 if that's what they gave us already as a freebie on this question. So thanks to that, all we need to do left to find is, because we don't know f of -5, we want to find that. We already know f of 1, we just need to find what that derivative is going to be equal to. And remember, because the f prime of x is already labeled as g of x for ourselves here, is that we just need to find the area underneath the graph of g from -5, again that x value from there, and x is -5 all the way to +1, keeping track of the negative areas and the positive areas to then run some algebra and give us our final answer. Okay, that sounds pretty nice to me. So let's move on with part B. It tells us now to evaluate from 1 to 6, the g of x dx. Okay, going from 1 to 6. Okay, so with that, we have a little bit of an issue, because we have this function splits between some linear graphs in terms of going from -5 to +3, which includes some of that limit from 1 to 6, as they stated here. But there is the next issue that from 3 to 6, and the second portion of this, we have an actual function to deal with. So we are going to have to do some separation of limits for ourselves here, because we need to make sure we can follow all the rules on this, knowing that if we split it from 1 to 3 of g of x dx and adding that with 3 to 6, we are still keeping in track of the exact value that they are asking for. But because this 3 to 6 on the limits, that will then allow us to use this exact equation, because they gave us from that limits of 3 to 6 for that curve, should be easy for us to find. Okay. Then of course this guy is just going to be directly from the graph. And so this is a graphical one, this is an equation one. That one to keep track of. Okay. So 1 to 3 though, they've already settled out for us. Again, that's this area right there from being 1 to 3 on the x, which is quite nice because that looks like just a lovely rectangle that is waiting to be found by us. Okay. So with that, with the 1 to 3, that is just going to be one single area with a base of 2 and a height of 2, so a nice square waiting for us. And then we need to add that with this new integral from 3 to 6 instead, which will be taken by the actual function itself, again, of the equation of 2 times x minus 4, all of that squared. Okay, dx. Alright, so with that, we have a 4 plus, now this integral needs to then be evaluated. So something that we can do here, just to keep ourselves a little bit easier, is that we get to keep a coefficient on the outside of 2. And I would like to FOIL this out so that we can then see what each guy is going to turn into. The FOIL is quite easy, so that allows us to follow the rest of the rules easily. The coefficient can leave on the outside, making it x to the third over 3 minus 4x squared plus 16x, and we range it from 3 to positive 6. Okay, so with that, we can run this function a bit further. So 4 plus 2 multiply all of. Now we need to run the actual limits of integration here. So 6 to the third power, starting with 36, should be 196, if we remember that properly. So 196 over 3 minus 4 times x squared, 4 times 36, 144, yeah, 144, plus 6 times 16 times 6 was going to be 96. And then we subtract it all, so make sure to keep all of them inside here. So 27 over 3 is a positive 9. That makes our lives a little bit easier there. Minus a 36 plus a, is that 48? Yeah, 48 at the end there. Okay. we have some algebra to work out and some very simple arithmetic, so there should be no problem for ourselves here. So 4 plus 2 multiply all of. The first parentheses, 144 and 96, that's going to be less than 50, that'll be 48, looks like, if you do that, yeah, 48, yep, okay. So this guy is a negative 48. Negative 48 times 3, though. Negative 48 times 3. Oh, 120. Oh, that's is that exactly 144 as well? If you do it by 3s? Yes, it is. Okay. So, which is going to be negative 144 over 3. Quite nice. Which, in this case, we can run the simple subtraction here, giving us 52. Yeah, 52 over 3. Okay, remaining there. Minus, now on the right side parentheses. 3648, that's a 12 difference right there. So with a positive 9 gives it a positive 21 to be subtracted. So we run this next line of work here. 21 over 3, that's 63, right? So 63 over 3. Subtracting that gives us a negative here. Negative. That's quite odd. Why are they giving us a negative area? That shouldn't be... That should not be there. We'll have to give that some thought in a later time, I suppose. That's a little bit odd why they're giving us a negative from that area, because that still does not make any sense to me. It still must be a positive, because everything is literally above the axis. 3 to 6. 36, 190... Wait. 36, wait. 36... It's not times 3, it's times 6. Oh, 216. Okay, my math was a little bit off. Okay. Gotta make sure we keep that up in check here. Because, yeah, it should be... Yeah, 216 should be divisible by 3. Yes, okay. So let's back up for a second here. Everything else seems to be still in order here. 36 times 4, 144. That still looks good. Yeah, okay. 216 gives us 72 as a result of that. So... that 52 over 3 is not valid there. So 72 minus 48 should be 30, 20, 24. Okay, so 24 minus 21, which is a positive 3. Okay, that's not too bad for that. So it's 4 plus 3, so that 63 over 3 doesn't matter to us. So 46 plus 6, 4 plus 6 as a result of that multiplication gives us a positive 10. Okay. A little bit messy there at the end, but still something that we are easily able to find out so that everything seems to make sense from our side. Okay, very good. Okay, so let's run to part C here. It says that for the interval negative 5 to x to 6 on what open intervals, if any, is the graph of f, both increasing and concave up. Increasing and concave up. Okay, good. So we have the two vocabulary words here, of course, increasing, concave up. Again, that is for the graph of f, meaning that they are looking to make sure that the first derivative of f is greater than 0. That is the increasing bit. And then the second derivative of f is greater than 0. That is the concave up. Okay, very nice. So because of that, we can go and see what that will look like on our side for these two results. Again, the first derivative, thankfully, is already given as g of x. So that must mean the second derivative is just going to be the derivative of g, which we can already see thanks to our graph of g at the start of the problem. Okay. So if we want the first derivative to be greater than 0, we need to look at all the spaces in which g is greater than 0, which is just going to be from the interval going from 0 all the way to 4. But it does not include the 0.4 because it touches 0, but we'll continue all the way to 6. Okay, so this interval goes from 0 to 4, does not include 4, but goes all the way to 6. Okay, and then for the first derivative of g, again, if this is what they're looking for, that just means that we are increasing on the slope of g. So with that, we have positive slopes going from this section right there on g, then it stops but continues right there, and then stops and continues once more over there. Okay, so to keep that in mind, we go from -2 to -1. That is increasing for g. Then we continue going from 0 to 1, and then lastly going from 4 to 6. Okay, so anything that will hold both of them together in that spot, well, that's going to be from 0 to 1 because that is included in 0 to 4, and lastly 4 to 6 because that is also included in the 4 is already included, okay, just want to make sure all of our points are correct. Okay, good. So that would just mean that we have the increasing and concave of both proven at the interval from 0 to 1 as well as 4 to 6 on those open intervals. Again, that's where f of x is increasing and concave up. Okay, we can box that off. We are running out of space, sadly, for part D, so let me quickly take a look here. Inflection point of the graph of f. Okay, I think we can just barely squeeze that in those last lines because that shouldn't be taken very quickly. Again, that's they want x coordinates of each inflection point of f. Okay. Yes, our boy Nicholas asks, what are we covering today, Mr. Lab Coat Guy? Yes, indeed. That is the title of the of the stream, but we have right now the 2018. This is actually the year after I graduated high school, but nonetheless still something posted by College Board. The 2018 free response questions. So far, we have actually already gone over to the first 2 problems of the calculators. So again, this is here. Question 1 to 2 is the calculator section. If I can spell that properly, the calculator. So that already is done. 18 out of 18. I'd say that's pretty good so far. So we are currently on problem number 3. We're trying to squeeze in part D here for this last section. So still, to continue forth, we are looking for inflection points on f itself. Again, meaning that we are looking for the second derivative of f to be equal to 0, but that also means that the first derivative of g is equal to 0 as well, because we have that relationship given to us on the equation that the g is the first derivative of f. Yes, Nicholas says, thank you for the recap. Of course, for anyone that comes in late, we can always do any sort of recap, because everyone's schedules are always busy. Nonetheless, though, we need to see, again, where that second derivative goes to 0, or in this case, g, the first derivative, also goes to 0, which means we need to find points in which we either find the changes in slope going to 0 or things of that slope. Okay, so points of inflection for the second derivative. Again, we need to see that change from a positive negative slope, which in this case will be 1 right here. So that is that x is equal to 4. We can see we were decreasing into an increase right there. Okay, and then I think there should be a few others here. Yeah, there should still be a few others, because we need to see ones where if we have the increase to decrease, because we have a lot of zeros to decreasing here, it looks like. But I think we should be still fine for that. So if we go right here with these other points, so we have corners here, here, there, and there, so that's a total of 6 points here. Let me just think about that for a quick second here, about that, to make sure we're looking at the same thing here. Yeah, okay. Yeah, so the corners wouldn't matter, I wouldn't say. When we think about the definition of inflection point, because the actual definition means that we need to change from a negative slope to a positive slope as seen at x equals 4, versus corners would not be considered for inflection points. So because of that, we only have really one here, x equals 4. Again, this is where the slope of g of x goes from negative to positive, right, at that exact point. Okay, so that will match exactly for us. We did fit indeed all 4 parts of this problem right into this page, so that should be good. So that was all of part 3. We'll finish problem number 4, and then we can get to the corrections after that. Okay. Good. So again, as a constant reminder, you can always send over all of your questions to the email right there, the labcodemath@gmail.com, or again, hit us up in the chat to see what is on the minds of our students here. But nonetheless, though, we'll go over to problem number 4, which has a lovely table for us. So we have the time in years. Make sure this is problem number 4. And then this is the h of t in meters. So let's run this table here. So it goes from in years 2, 3, 5, 7, 10. 3, 5, 7, and 10. Okay. And so 1.5, 2, and 6. 2 and 6, 11 and 15. Okay. So as context here, it says us that the height of a tree at time of t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Okay, and we have the values given on the table. Okay, so with problem A, it says here to use the data to estimate h prime of 6, and then using correct units, interpret the meaning of h prime of 6 in the context of the problem. Okay, very good. All right, so we got to do a little bit of an estimation here for h prime of 6. Again, thankfully, because 6 is right in between the table of 5 and 7 for that first derivative, while they only give points for the original function h. This just means that we are looking for average rate of change as a good way to estimate. Average rate of change, again, is a perfect way to estimate in terms of having just points on the original function. Okay, so what that will look like for us is that we can then take the points of h of 7 minus h of 5, dividing it all by the change in the x values of 7 minus 5. Good. Okay, so we take the actual h of t values and then subtract it between the difference of the t values. We should get what we are looking for here. With the correct plugin, we get this as a result, 11 minus 6 all over 7 minus 5, which will give us a positive 5 over a positive 2. And I think that should be fine in terms of the result of the answer in an improper fraction. But what that means is that if we have meters and in years that we divided by, that's just going to be meters on top per year as the units. Okay, that's the first part of that problem done. But they want to interpret the meaning here. Again, that's going to be the estimate of the rate of change in height in meters per year for the tree. Very good. And that should give us all the things that we are looking for on this problem. Okay. So again, just to recap here is that we have the average rate of change given, again, because we're looking to estimate the first derivative of just a series of points on the function, which just means we just got to do a simple slope function because we're estimating slope between two known points, getting the result and giving a very good reason as to why that would work for the units of meters per year once we do the actual unit conversion ourselves. Okay. Then part B says here, explain why there must be at least one time in terms of t for the interval of 2 between t to 10 such that h prime of t is equal to 2. Oh yes, I do believe with this kind of a question that we are looking to guarantee must be at least one. That's a guarantee if you ask me, of h prime of t being equal to 2 for our function. Oh boy, that smells a lot like our good old friend MVT, our mean value theorem, guaranteeing certain values on the first derivative function, right? So what we can do is that we can then take a look, we need to take a look again at average rate of change to make sure that we are talking on the right steps here between those two endpoints of 2 and 10 that they gave us that we want to look at. So we run the same similar equation between the two, just that we change the actual values of t for ourselves. So with that we get 15 minus 1.5 over 10 minus 2, which is 8. Geez, why they do give us 1.5 like that? That's a little bit unfortunate. Just as a nice reminder, that's going to be 3 over 2 in terms of a fraction. Makes our life so much easier. So with 15 being a nice 30 over 2, we will then see that it's 30 over 2 minus 3 over 2, so that's 27 over 2, all over 8 still. And so with that, we just get a lovely 27 over 16. Again, that is going to be meters per year in terms of the units. Okay. And what are they going on about here? 1.5 and 15, yeah. 2. I think they might be confused here because that is not going to be the case for this. 4 and 2, but 4 and 2 that way. Okay, so this is no good because we want this to equal to actually 2. So we can't take their word for it being exactly between 2 and 10, but we can take another look here. Is that if we then instead took the difference between 6 and 2, or 3 and 5 that is, 3 and 5, or I'm messing that up. It's the highest minus low, so h of 5 minus h of 3 all over the 5 minus 3 in terms of those 2 points, which is still inside the interval of 2 to 10. That should still be enough for us to work with, because if we took a look at those points, we have a height of 6 minus 2 over another 2, which gives us 4 over 2, which is exactly the 2 meters per year that they are looking for. Okay, so unfortunately, because of the points they gave us, they try to mislead us with mean value theorem, but this is indeed what we want to look at. So again, that's between 3 and 5 for t, and that's not the right way of writing it, for t, between 3 and 5, but that is still good enough for us to keep in mind for all that we are looking for, because that's still within the interval. Okay, so again, according to mean value theorem, okay, because the average rate of change for h of t between the two limits, h of 5 and h of 3, is the 2 meters per year. Again, it guarantees that there is a t such that the h prime of t is equal to 2 on the interval going from 3 to 5, which is inside of that larger interval they're looking for, 2 to 10. We just kind of have to shorten our search a little bit, but with that, we do have exactly what we need to confirm that part B is not crazy and that we have exactly what we need thanks to mean value theorem. So again, for this, we have to keep in mind that they did kind of screw us a little bit with saying that they want to look between 2 and 10 as intervals. If we actually took the interval, it didn't really match up with the rate of change that they're looking for. So just by decreasing that scope, we do get the exact rate of change that we want. So mean value theorem still works because it's still within that limit of 2 to 10. It's just that we had to refine our search a little bit more to get what we were looking for. Okay, part C says to use a trapezoid, trapezoidal sum with 4 subintervals. From the table to approximate the height of the tree over the interval from 2 to 10. Okay, very good. So trapezoidal sum, that is indeed something that I have very clearly taught in one of my previous channel videos on Riemann sums. So this should definitely come without any sort of issue for us. 4 subintervals, four different trapezoids here. As you can see, with 5 points, we can definitely make that between grouping, pairing every step of the way. So those will be the 4 subintervals for the trapezoids. So because of that, we get to run this through, with this being the 4 different types. So we have the bases and heights. So the base for the first one is just going to be a base of 1. The heights being the 2 plus 1.5 all over 2. We just need to add the 2 heights and take its average. And we go with the next one with the base of 2, 2 plus 6 all over 2. And then the next base is another 2, 6 plus 11 all over 2. And lastly, the last base is a 3 with 11 plus 15 all over 2 with that one. Okay, that's how we set up a trapezoidal Riemann sum on this. And so we just run this straight through. Let's see here. So 3 halves, adding with 4 halves is 7 halves, so 7 over 7. 7 over 4. So the halves there. Okay. Thankfully, those 2's will cancel out. That's just a whole 8. Those 2's cancel out. That's a whole 17. And let's see. So 11 and 15 gives it 26. Gives it a whole 13 after divide by 2, so makes it 39. Okay, so let's add everything here together. The 704 will wait while all the whole numbers get to play first here. 25 and 39 gives us a 64. Yep. Okay. So, unfortunately, though, this doesn't look like it's going to play any nicer than this. So, 604 times 4 is 256 all over 4. So, in terms of a mixed number, in terms of improper fraction, it's going to be 263 over 4 meters. Yeah, I think they prefer to have the improper fraction. If it really had to give a mixed number, we can shove off 1 in the improper fraction, 65 and 3/4 of a meter. Okay, both of them should be fine. I think the AP test graders prefer the improper fraction. So with that, the work should match up accordingly. We had exactly the 4 subintervals. Again, trapezoidal just means we pair up 2 heights. We take the average going down across the entire interval. And with that, we should be able to result in exactly what we're looking for. So we get the total height in the meters there, and that will be part C. And let's take a look lastly at part D, and that will be enough for question number 4. Okay, so the height is given by a new function, capital G of x is equal to 100x all over 1 plus x, okay, where x is the inside diameter of the base of the tree. Okay, and so let's see in meters. Let me make sure that we have that. Okay. So it says here that when the tree is 50 meters tall, the diameter of the base is increasing at 0.03 meters per year. Okay, so according to the model, let's see, what is the rate of change of the height with respect to time? Okay, so what is the change of height of the tree respect to time? Okay, and then at what time? At the time. Okay, see, at the time the tree is 50 meters tall. Okay, so we got a little bit going on here, so let's just take this one step at a time. So again, we have a new height of the tree, g of x, now in this equation, but we also have the new variable that x is the inside diameter of the tree. Okay, so they do give us a rate at which the diameter is increasing in meters per year at a very specific height of the tree. And so with that exact height of that 50 meters, we want to see the actual change in the height of the tree in respect to that. Okay, so one thing that we can note here is that we already have, it looks like, the 50 that we're looking for. So again, at 50 meters of height, which is the g of x, we have 100x over 1 plus x. So thankfully this is a very simple thing to find out, because if that's the case, the x is equal to 1, because that makes it 100 over 2 equal to 50. So again, that's 1 meter in the diameter of the tree. Pretty easy for us to solve. They didn't tell us that explicitly, but that's pretty easy for us to solve. The issue, of course, is that they want to find the rate of change of the height of the tree, which will then mean, of course, is that we will need to find the difference of g respect to time. Okay, so because of that, and we have a lovely first derivative implicitly of g and x, because of the two different values of the function here, and that there is a change again. So in this case, we do have a dx over dt as a 0.03, as they mentioned. We will then have to take the derivative of that g function, and we will have to go bring up our good friend quotient rule on this equation for us to solve that. So we will have to do exactly that, just so we can isolate d of g, because again, they're looking for that, especially at that time at x is equal to 1. So we will run this through. So it's going to be that low, so 1 plus x, derivative of high, which is going to be 100 dx over dt, subtracted by the high, which is 100 just x, derivative of low, which is dx over dt on its own, all divided by 1 plus x, all of that squared. Not too bad. I know quotient rule is quite something that many people would be struggling with on their work. But for those that know the rule by heart, it shouldn't be that hard in itself. We have everything we need to plug in for. dx over dt we already have, and we have the x being a 1 meter diameter that we simply solved for before as well. So with that, we can then go ahead and start plugging everything in here. So we have a 2 in the first parentheses, 100 times a 0.03, okay, subtracted by a 100 times a 1, and then multiplied by 0.03, all over 1 plus x squared, which is just going to be 2 squared on the bottom. Okay, we'll run some of these problems here. We have just enough space to fit this right in here again. So 100 times 0.03 is just a whole 3. Same thing here. This guy all on the left side is just going to be another whole 3 over there. So that's going to be 6 minus 3 on the numerator. I'll simplify it out, divided by a 4, which will then be a 3 over 4. Again, that's dg over dt, so that's going to be the height in meters per year for the height change. Okay, now it was the rate at which the tree was growing when we know the inside diameter of that tree. Okay, so that should about do it for part D there. Again, we had to just do a little bit of implicit differentiation with some quotient rule, but everything seemed to work out on its own. So we have everything we need for part 4, And so with that, we should be able to start correcting these next two parts. Okay, so we're going back to our questions here on the answer sheet, and we shall see how that looks like for us. So going back to problem 3 with that graph that we're dealing with part A, we're looking through, and there we have a little bit of something going on here already. Okay, so we set up the integral exactly the way that they wanted to, with the g of x of integral from 1 to -5. Interesting. Then did they flip that? I mean, well, they flipped it just because it became negative anyways. 19/2. Huh. From -5 to +1 is 19/2. We'll take a look at that in just a second. But the setup is exactly correct. The answer is not, though. So let's make sure we're looking at this thing properly here. So with this guy from -5 to +1, we still have, again, let me make sure we're looking at this properly, because we had that rectangle here, this rectangle back here, which has a base of 3 and a height of 3. Base and height of 3. Is that what I wrote down here? No, I chose a base of 4 because I counted incorrectly. That's just hilarious. So that's a -9 there, with the height of -3, and this will be -3/2, and this will be a +1 there. So all the way to 1, subtracting that is -1/2. So yeah, that's -19/2 for the integral. Okay, and that is where everything went down the drain, sadly. Because of that, with this being -19/2, then just by sliding everything over there, f of 1 was going to give us a +3, and then moving over is a +19/2, which is 25/2. That should have been correct instead. Okay, unfortunately, another silly mistake gets to you, and a computational error of simply counting tick marks really is the big killer in all this. Isn't that hilarious? But that is still 1/2 correct for part A, because the setup was good. It's just that the actual arithmetic was not, and simply counting tick marks apparently is a little bit too hard for me even after the calculator section. So we'll continue forward still. So part B, we will be evaluating here. That, as a result, we're going to split between the 3, so that's exactly what they want to see right there. And we run the actual integration of that function of g of x from that section right there. So +10 being the result of that answer is exactly what they're looking for. That's all 3 out of 3 correct for that part. Okay, and then we have part C here. So our intervals here from 0 to 1 to 4 to 6. That's exactly what they're looking for. Reason, of course, is that, yes, we're looking for the increase on g of x, and indeed staying above 0 on g of x itself as well. So that's 2 out of 2 correct for us there. And lastly here, so we have an inflection at x is equal to 4 is the correct answer only. Again, we want to change from negative positive on that function g of x. That's what they're looking for as well. So that's 2 out of 2 correct, to prove that we were looking at a point of inflection for that graph of f. Okay, so because of that, we got everything but 1 wrong. So well, 1 correct, that is. So that's 8 out of 9 for that page. We'll keep that in track with our packet here. That will be 8 out of 9 points for question number 3. And we will move forward with question number 4. And slightly bummed that we made a little counting error, but that is something to continue to prove to us that when you are taking the test, you do have the whole time to make sure you're counting everything properly. And if our camera would like to focus on this, that'll be really nice. If our there is plenty of lighting on this thing here. I don't know what the deal is. I mean, if I really have to just like correct from up here, I will have to. Let's see, maybe wants my hand in the frame just so we can look at my hand. There you go. Thank you. Okay. Very nice. All right. So going on to question number 4 here. We have things that we worked on here with the average change of h to estimate h prime of 6 at 5/2. That's exactly what we want. The meters per year, again, there's the average change of the height of the tree for that. So that gives us all 2 out of 2 points for part A, for that function for the tree. Okay, so yes, they did point out that we were supposed to do the average rate of change of between 3 and 5 instead, because of how 2 and 10 is not the actual correct interval for us to guarantee it. But because 3 and 5 was in between the 2 and 10, which they asked for, that does guarantee it for that spot. So using the mean value theorem as a conclusion, that's exactly what they want us to do. So that is 2 out of 2 points for part B, correct. All right. Then for part C, we were going to do trapezoidal sum here. And what in the world is happening here? Average height. Wow, okay, yeah, we are once again running into some problems here because we were supposed to do in terms of average height. Okay. That is sad, because it's not, yep, I wrote down the problem wrong, that they are looking for the average height, meaning that we did all of this in terms of the integration. We had to set it up with 1 over 8 as the next part to make it an average height, not the total height of the tree across the different intervals. So that is quite unfortunate. That is another point missed, so that makes it 1 out of 2 correct. The trapezoidal sum was exactly correct. Actually getting all of this was completely correct. It's just multiplying the 1 over 8 had to be the last step to make it over 32. That is quite sad. Another oversight because we are not being careful enough. But still, we get to move on to part D. That we are looking for the actual integration here. So we get 2 points for taking these specific derivative of g of x for that. So we did do quotient rule correctly, and we get the answer of 3 over 4. Okay. They actually put a note down here that you only get 1 out of 3 points if you did not do chain rule properly, but we did exactly that just fine. So running the the derivative was exactly the way that we should have. So that makes it 3 out of 2, either out of 3 correct for this section. Okay, we got the entire derivative down correctly. That was 2 points, and the 3 over 4 for that last answer is indeed what they're looking for. So another section where we missed 1 point, leaving us at 8 out of 9 for question number 4. So we started strong. We're kind of dropping a little bit of detail here at the next 2 parts, but we can definitely pick it up on question 5 and 6 as we close everything out here in our last section. Okay, so that's something that we will keep track of for ourselves as we move along here. Okay, so hopefully this will be a good lesson for all that is watching, that indeed there are just slight mistakes that will make the difference between full points or less points on the actual exam. So with that, we should have everything we need to get to our last points here at questions 5 and 6. And that will conclude it for today's stream for us running through the 2018 AP Calculus exam. Okay. So at question 5 here, it says here that let the function f of x be defined at e raised to the x times cosine of x. It's a very classic equation right there. But it says here that we need to find the average rate of change of f on the interval from 0 to x to pi. Okay, so with that average rate of change, so going from there, looks like we will just have to do very simple average rate of change problem. Looks like that's all we need to do. So let's go from f of pi minus f of 0 all over pi minus 0. We just leave everything in terms of the fractions and pi's here. So with that, we have e raised to the pi times cosine of pi minus e raised to the 0 times cosine of 0 all over pi minus 0. Okay, so with that, that will run quite easily. Cosine of 0 is just going to be a positive 1. E to the 0 is also another positive 1. Cosine of pi is a negative 1. E to the pi will stay exactly the same. So that's negative e to the pi minus a 1 all over pi. And that's it. It looks a bit odd, but we're using our good old constants and irrational numbers here. We just leave it as such, and that's it. Okay. So let's have a look here. Next is that they're asking what is the slope of the line tangent to the graph of f at x is equal to 3 pi over 2. Okay, so slope of the line tangent, that would mean that we will need our first derivative to come in clutch here for us to then determine some exact values of x is equal to 3 pi over 2. So we take the first derivative right here of f of x, something we can very easily do by hand with good old product rule. So that's e to the x of cosine of x. That's the e to the x taking the derivative of. Now we just subtract with e to the x times sine of x because cosine goes to negative sine in terms of a derivative. Okay? So in order to find the slope, our slope of the line is going to be the f prime at 3 pi over 2 for us. So we plug that guy right in there. So e raised to 3 pi over 2 multiplied by cosine of 3 pi over 2 subtracted by e raised to 3 pi over 2 multiplied by sine of 3 pi over 2. Okay. 3 pi over 2, for those who simply do not remember on the unit circle, if we were to draw it real quick in our minds, 3 pi over 2 is that guy right there on the negative 1 on the y. Again, coordinate wise, that's going to be 0, comma, negative 1. That is 3 pi over 2. So because of that, cosine, this entire guy goes straight to 0 because of that. The sine of 3 pi over 2 is negative 1 on that, making that guy positive. So our slope then will be evaluated at a positive e raised to the 3 pi over 2. Very nice for us. Okay, and our camera just decided to stop liking our focus here, so would you mind coming back? All right. So with that being the 3 pi over 2 right there, then we will then need to do the AP test graders like point slope a lot better. So all we need to do is run the point at f of 3 pi over 2 for us to find the y value. They gave us x value, we just got to find the y value here. So e raised to 3 pi over 2 times the cosine of 3 pi over 2. Would you look at that? This actually goes all to 0 because it's cosine of 3 pi over 2. So our point here is going to be 3 pi over 2 comma 0 for us. So in that case, that's going to be a y is equal to the slope of 3 pi over 2 multiplied by x minus, let's see here, so we just do the point itself, that's e raised to 3 pi over 2, that's a slope. So 3 pi over 2 is the x value and then plus a 0 because the y, there is no y-intercept, at least in that sense, for point slope form. And so with that, this will be the result of the line being tangent to that point. Okay. Again, as a quick recap, if you want to find the line tangent equation, that just means that we need it in the form as y is equal to m times x minus h plus k, like this, in point slope form. That's the easiest way in which the test graders like to look for it. And so we just need to find the actual slope, which is going to be the derivative at that point. And then we need to find the coordinates for which x was being given to us for at that exact point. And then you plug in the rest. Very easy on that sense. So then on part C, they want us to find the absolute minimum value of f on the interval from 0 to x to 2 pi. Okay, so absolute minimum, well, we got to show all of our work for that, meaning that we need to then see where that function f prime of x, again, needs to cross 0. Again, we need to do a number line analysis for this, such that we can then see some relative minimums for ourselves. Okay, so again, this is not graphing, so we will have to just take a look at this. So between 0 to 2 pi, given that we already have our first derivative graph right here. So we have it f prime of x is equal to e times x times cosine of x minus e to the x times sine of x. Okay. We can then go ahead and see what that will look like for ourselves on that. I think we have a couple ways of actually doing this. And wow, okay, we have Nabil Aziz coming back into the chat saying, remember me? Yes, I do. I believe you left a comment on one of my lecture videos. very kindly telling me to keep up that work. Yes, of course. We cannot forget our friend all the way from Bangladesh tuning into our live stream. So we'll see if Nabil has anything to say for us today. But we're still working on problem number 5 out of 6. He just came in through this last third of this exam. So we're still in the process of trying to see where we can confirm where the zeros are on the first derivative graph. So let's try to make sure we are on the same page about that. I think with something like this, it would be equal to, yeah, so we get zeros when the cosine is equal to sine of x, because given that e to the x is the common factor on the outside of cosine of x minus sine of x, we just need to find the spots in which those two are equal values to each other so that we get 0 inside of that parentheses, because e to the x will never go to 0 thanks to an exponential. Alright, so because of that, the times in which cosine and sine are exactly equal to each other would only happen on 2 places, which are going to be in the unit circle between the 2 parts of pi over 4 and it's the 5 pi over 4 on the third quadrant. So first and third quadrant, those are the only 2 times sine and cosine will be equal to each other. Some very good pre-calculus memory that we need to have on this point here. So we have those 2 points that we can then test for. So at pi over 4 and 5 pi over 4. Okay, this is where we can go and make sure to see that we have any positives or negatives coming out of that. Okay, so we already have one of them already actually, because the previous part of part B was asking us to find the slope at 3 pi over 2. 3 pi over 2 will be a little bit beyond 5 pi over 4 in terms of the unit circle. So on that sense, that was a positive slope that ended up there. Then we can check out some other points here. So pi will be in between there, and then a nice 0 will be in between there as well. Okay, those are some values that we can see. And with that, we can go together to see what we are looking at in terms of this type of problem. Now, Nabil asks, how long am I doing this? Well, the description should actually say that I've been live for close to 2 hours now for today's live stream. And yeah, we started about 2 hours ago, and we are nearing the last third of this exam. And so with this, we have exactly the point that we need to look at pi. So in terms of if we plugged in for pi, that's cosine of pi minus the sine of pi. Okay, so sine of pi will give us 0. Cosine of pi is going to be -1. So that's a negative on that sense. And we plug in the zeros for that last point to look at the sine. Cosine of 0 minus sine of 0. In that point, sine will go to 0, and cosine of 0 will be a +1. So we have the number line analysis complete. Nicholas tells us that we need to finish strong, which I totally agree. We have just a few more problems to go, and that will conclude for this 2018 exam. I think we might be nearing one of the highest scores that I've gotten before. So hopefully, we keep everything very focused here, we should be very good to match exactly what we need to break a record here. So with that, we have here, if you can see, that we have a switch between a negative to the positive on the first derivative. Again, this is the first derivative analysis on the number line. So at x is equal to 5 pi over 4, that's going to be a relative minimum. Okay. Which means that with that, we have a few other things to keep track of, which will now be the actual endpoints at 0 and 2 pi. For us to then find where so these are endpoints, again, because those can also be possible candidates for an absolute maximum or minimum. So we need to keep track of that for ourselves as well. Okay. So with 5 pi over 4, we can just plug that straight into our equation here. So that'll be e raised to the 5 pi over 4 multiplied by cosine of 5 pi over 4. Okay. Then at 0, we have e of 0 times cosine of 0, and same thing, e of 2 pi multiplied by cosine of 2 pi. Okay. So because of that, we will then end up with some of these points right here. So e to 0 cosine of 0, that's going to be just a +1. E to 2 pi times cosine 2 pi, that's going to be just e raised to the 2 pi power. And then lastly, e to the 5 over cosine of 5 pi over 4. 5 pi over 4, that will give us, that'll be negative, yes, so negative rad 2 over 2. Rad 2 over 2 times e to the 5 pi over 4. Now, with that, I don't think pi will give us a negative because that makes it smaller than one negative full pi. Why isn't pi a possible solution? Because it's not equal to 0. That's why. Okay. Well, Nabil asks, do I know Nicholas as a person? Actually, the answer is yes, indeed. Nicholas is one of my friends who actually went with me to college. So that should be enough for that, I think, on this problem. Because, yeah, so with that, the only negative answer is going to be this one at x is equal to 5 pi over 4. Again, so that's going to be the f of 5 pi over 4, which is going to be equal to negative rad 2 over 2 e to the 5 pi over 4. There you go. So this is going to be the absolute minimum after all of our work to prove that this is the best candidate for this problem. Okay, so with that, we have one last problem to go over, part D, and we'll see how that goes. Okay, so it says here that we will let G be a differentiable function such that G of pi over 2 is equal to 0. So it says here that the graph of G prime, let's see, is given below. So it says here, oh, very interesting. So now they want us to find the limit as x approaches pi over 2 of f of x over g of x, or state it doesn't exist. Okay, very good. So we have ourselves, they give us a graph here already on specifically just on part D, that we have this little curl here. So here's at pi over 2, and then we go to 2 points at pi, and then ending at 3 pi over 2, and then 2 pi. So we go 1 and 2 right there. So we curl up something like this at pi over 2, and then we go straight all the way down past 3 pi over 2 and ending a little bit underneath the 2 pi, something like this. Okay, this is g prime of x shown on that graph. Okay, so we need to then see what this looks like for ourselves. Okay, so if we looked at the limit already, we have something that we might note here is that at f of x over g of x. So if we plug this straight in, knowing that this is a limit as we approach a specific number, if we just plug that in straight away at f of pi over 2 all over g of pi over 2, they told us already that the g of pi over 2 is already 0. That's already 0 in the denominator. But f of pi over 2 is going to be e to the pi over 2 multiplied by cosine of pi over 2, which this already gives us 0 again. We end up with 0 over 0 in the limit. Now, some students might think, oh, that just means that the limit doesn't exist. That is very not true. This is an indeterminate form, so we cannot determine whether this limit exists or not. We need to go back to our L'Hopital's rule, because this is something that should have been learned kind of early or kind of later as well, is that when we're evaluating limits that are 0 over 0, or in other cases like infinity over infinity, we have an indeterminate form which we cannot determine the answer until we go and run L'Hopital's rule. So by doing so with this notation is that we keep the same limit, but then we take the derivative of both the high and low part of the fraction for us to determine the rate at which either the numerator or denominator is going, so then we could determine where the limit is going to take us. Okay, that's a very simple rule that we can do for ourselves, and thankfully because they gave us the function of g prime of x, we can then see what that looks like. So at pi over 2, it is a positive 2 on the denominator. Then f prime of pi over 2 means that we have to take that first derivative of e raised to the pi over 2 times cosine of pi over 2 subtracted by all of e raised to the pi over 2 multiplied by sine of pi over 2. Okay, so with that, this left hand side with the cosine of pi over 2, that all goes to 0 thanks to some easy unit circle remembering here. But the sine of pi over 2 gives us a positive 1 because of that. So we do actually end up with a determined limit here of a negative e raised to this pi over 2 power all over a positive 2. And that will be the result. Again, L'Hopital's rule, which is a very important rule for ourselves here, is that we can then take the limits of both a function that is indeterminate in terms of a ratio, but then actually determine the final result of it after taking the derivative of top and bottom of it. A very simple rule which has a very simple requirement that it needs to be in an indeterminate form first for us to make that acknowledgement. Okay, so we'll get over to part 6 here, our last question for the night. But we have our friend Nabil asking, what type of friend is Nicholas, like introvert or extrovert? That is a great question. I believe Nicholas will have to answer that for himself if he's willing to. If I were to give it a question, give it an answer, I would say Nicholas is more of an extrovert in that sense. But that's just my own experience. That's something that he'll have to answer himself if he's willing to in the chat. Nonetheless, though, let's go over to part 6 here. Nicholas says that he's bored. Yes, indeed. I believe that is also quite true. But in any sense, though, in my opinion, he'll be more in the extroverted side, although many people might not think of it that way. But at least to me, in terms of the definition of an extrovert being someone that actually gets energized in the presence of other people, I think that will be the case for him. But in any case, though, let me write down the question for part 6. And I think we actually have to do one part of it on the packet itself, as we've done before. But we have this differential equation, dy over dx, of this, written out right here. But to show, we have a slope field question, something that we've done multiple times, that they continue to ask us at least once in each of these packets here. So we have the slope field defined out below. And so we need to sketch the solution curve that will go through something like this. So they gave this to us. So they also have 2 points, the 0, 2 and 1, 0 on this field. And so we just need to give a proper solution curve that would match for what is going on over here. Okay. So because of that, we can go knowing that we pass through point of 2 right there, that 0, 2 at a 0 slope. We need to keep that in mind for ourselves. And at 1, 0, we have a slope that goes a little bit positive 1, kind of like this. Okay. So with that, we can go and start putting things through here. So let's see here. We have something known as a little bit of a going down. So it's negative, going to 0, and then going back up positive. So we have, I think, something that is possible here is that we end up with, let's see, because it goes positive right after the fact here. Yeah, so we have a negative slope here, so we go down, and then we start at, well, let's see here. Because it gives us a, we need to pass through that, and then we need to also pass through 1, 0, even though it doesn't have any, for the reason, it doesn't have any negative slopes going at 1, 0. Let me think about that for just a second here, because this is not exactly adding up, because we need to drop down without a negative slope. Very odd. Okay. But in any case, though, I think we should give something that should be quite similar here, in the sense that we can go and start saying that we have a negative slope going down, we pass through 0, 2, and then at the 1 we kind of slope upwards as we pass through that. Okay. Yeah, I think something like this should be able to match, because we keep that slope all the way through, kind of like that. Okay. A little bit messy, but should be something that will match what we're doing here. Okay. All right. Good. So that's just all of part A. We give a possible solution curve. This one's kind of a little bit of a different subject here that we can math through. But at part B here, we can then answer in the next part. So it says here that let y is equal to f of x be the particular solution to the given differential equation with initial condition f of 1 is equal to 0. So it says here that we must write an equation for the line tangent to the graph of y is equal to f of x at x is equal to 1, and then use that equation to approximate f of 0.7. Okay, so we have this right here. Wow, Nabil is asking a very interesting question, asking if Nicholas is in a relationship. That is something that Nicholas have to answer on his own. Right now, we are very close to finishing this, and I would need to see what my grade will look like on this sense. Okay, so we have an initial condition here that they gave us at f of 1 being equal to 0. And so let's see what that line tangent graph is at that point at x equals 1, and then we must give the approximation of 0.7 from that line. So because of that, again, we have that point of 1 comma 0, and we need to put that in through the differential equation to find the slope, because again, that will be our slope for this problem with dy over dx giving us a proper slope, plugging in for 1 comma 0 on that steps here. So it's be 1/3 multiplied by x, and then 0 minus 2 raised to the second power for that. And so with that, we have some very simple arithmetic to go through, that we have a 1/3 multiplied by a positive 4, which will then give us a positive 4/3 slope, which then that equates to our slope. And so our line equation, very simply, is going to be y is equal to 4/3 multiplied by x minus 1 plus a 0 on that point, giving us point slope form. Okay. Yes, wow, Nicholas did give quite the great response, saying that he's got his girlfriend in Brazil, although math is better than girls. Now that is quite the good answer, Nicholas. I would applaud you on that one. Okay, so this is our line tangent equation right there, of y equals to 4/3 multiplied by x minus 1. But then we're not done just yet, because we need to do an approximation of the f of 0.7. So we need to plug that in for the point of x, so 0.7 minus 1, which will give us 4/3 multiplied by a negative 0.3, which this is terrible because they want us to multiply decimal by a fraction. We will say absolutely not, change that to a negative 3/10 for ourselves. Very nice, because we can run some cross canceling here with some easy algebra moves right there. So we end up with a negative 2/5 as the approximation of f of 0.7. Okay, very good. So that matches everything that we need on this side. So that will be part B. And lastly, our final part right here says that we must find the particular solution of y is equal to f of x to the differential equation with initial condition of f of 1 being equal to 0. Okay. Wow, Nabil says that he loves math too, and because that he is single right now. Wow, that is a little bit unfortunate on that sense, but nonetheless though, it is very good that we have other enjoyers of math, at least for me, because I do teach a lot of other students on the side, and the common response that I get is that they absolutely despise math. But with that, we definitely have math to keep ourselves company as we finish this last part of this calculus exam. So we need a differential equation to be given back as an original function. So let's take a look at that. So the dy over dx that they gave us earlier, as it was 1/3 x multiplied by y minus 2 all to the second power. So looks like we need to do some very easy separation of variables here so that we can go and take an integral of both sides of the equation. So we just multiply across, the dx going over to the right side while the y minus 2, all of that square needs to go back over to the left side. So from here, we can then take the integral of both sides of this equation, and then we can see what this looks like with our initial condition. So with y minus 2 raised to the second power, all in the denominator, that just means we have a y minus 2 raised to the -1 power as a result. We keep a negative there for the exponent rule when it comes back down, and then have it equal to 1/6x to the second power with the change in coefficient for the exponent rule on that side, and then a plus c because this is an indefinite integral at this time. Okay, so with that we can then solve for c immediately. So we just plug in for the point of 1, 0, which is what they gave us at the start of this problem. So with that we get a -0 minus 2 raised to the -1 power, 1/6, 1 squared plus c. We just need to solve for everything else right now. So we get a positive 1/2 as a result of that exponent on the left side. Then we get a positive 1/6 on the right side plus a c. So with that, the 1/2 goes to 3/6 for us to be able to measure this out on the same denominator. So c will be equal to 2/6 or 1/3 as a result of solving for c from that. And then from there, we should then be able to isolate the y on its own. So going back one more time, it's -1 over y minus 2. All of that, it's just 1 minus y to 2, just like that. And then we have 1/6x squared plus a 1/3. Okay, so with that, we just need to then throw everything into an inverse here, or in terms of a reciprocal, just so that the -y minus 2 goes back to the numerator, and then we shove literally everything else into the denominator for the time being. Again, this can look as messy as it needs to just so that y can be on its own. So we throw off the negative to keep it on its own right there, and then lastly we just add the 2, so it's -1. Well, yeah, I can put the 2 on the other side, it doesn't really matter. So we make a nice big fraction bar, and then we add a 2 at the end. And this would actually be the result of the differential equation with the initial condition that they asked for at the start. Okay, a little bit of work there, but it should be all that we need for now for us to then continue going forth through this. Okay. All right, Nabil is asking Nicholas some direct questions, so we'll see if Nicholas is willing to play some of the guessing games Nabil likes to ask when he comes through my chat. All right, but we will then go back to questions 5 and 6 and correct them, and we shall see what our final score will look like through our working through these types of problems. So let's first go, if I can get to it, the answers to question number 5. So this was with that first function that they gave us right here. Okay, and so we end up with a -e raised to the pi minus 1 all over pi. That answer is exactly what they are looking for after doing the average change. So that's a 1 out of 1 correct for us on part number 5a. Yes, Nicholas gave a great answer of a 7-foot, 24-year-old Giga Chad. Some very nice English lingo in America, which doesn't exactly match. I don't know if Nabil would understand all of that from where he is from on the other side of the world. But nonetheless, though, that is all that we needed for part A. Going to part B, we wanted that derivative then to be equal to the, let's see, if we ran the derivative, yeah, this will give us the slope of the e raised to the pi over 2. Then they just wanted just the slope tangent. That's all they wanted. Okay. And so by taking that derivative, that's exactly what we needed to do on this part. So that is both parts that were needed, the slope and the actual derivative. So that is going to be 2 out of 2 correct for part B. Okay. And so going to part C here, We will then go and check all the different parts here that we were looking for as possible candidates. So at pi over 4 and 5 pi over 4, okay. I don't exactly know why they think pi over 4 is a good candidate given that it goes positive to negative. But nonetheless though, looks like we have everything that we need because we have to set that derivative equal to 0, which is exactly what we did back in this step to make sure that we were reaching zeros on that derivative in itself. So that's 1 point right there. And then to identify that with our table, again, all the possible candidates for what we're looking for, that is another point that they're looking for right there. And of course, we have the true absolute minimum at the rad 2 over 2 e raised to the 5 pi over 4. That is indeed the correct answer to prove that that was the absolute minimum. So that is 3 out of 3 correct for us on part C. Okay. And then lastly, we have part D here, that we have a limit as x approaches pi over 2. Again, this guy, we end up with that indeed we have to point out that we will use L'Hopital's rule. Again, of course, g of x was already continuous given that they gave us that derivative that we kept in track of the whole time. And so we have ourselves the final answer of negative e raised to pi over 2 over 2. That is exactly what they were looking for as a result of us using L'Hopital's rule, given that we ended up with first an indeterminate form of this limit, meaning that we had to take the derivative of both the top and bottom part of that fraction for us to actually determine where that relationship of that limit was going to go. So that is going to be 3 out of 3 correct for us. So that is very good that we got everything that we needed to on all parts from parts 1 to 4. So that is 9 out of 9 for this part, meaning that we get to take a note on that on question number 5 here. So we have one last one to go. And yes, wow, Nabil is giving out about his age and height. Wow, 6 feet tall for 17. That's quite something. But anyways, though, we have our last section here for question number 6. So we have that curvature, which doesn't exactly match up exactly what I have here. Is that two different? Ah, okay. So it looks like I kind of dropped the ball on this one. We were supposed to show actually two different. The wording wasn't very clear for me as well. So, because he says sketch first point that goes to 0 to 2, and then sketch the next one that goes to 1, 0. They actually were looking for two separate curves. So it looks like we have one that just goes straight all the way across without a problem right there, and then we have the next one that will follow this downwards curve like that on the second one. I believe I did get tripped up on that when I was going over this with a different student quite a while ago. So, Nicholas, this is not a good time to lie that you're saying that you're my senior. That is not correct. We graduated in the same year. I don't know what you're talking about. Okay. Anyways, though, we have ourselves two different curves that needed to be drawn. So unfortunately, I kind of dropped it on that one. So that's part A. Would actually get me 0 points because I needed to draw two separate curves. It would have been nice if they actually showed that it should go through both of them. Nonetheless, though, we'll have ourselves part B right here. That we have the equation of the tangent line shown as y is equal to 4/3 x minus 1 multiplied. That's exactly what they were looking for. And then the approximation of the negative 2 or 5. Again, they showed a decimal of negative 0.4, but that's literally the same in the fraction form, so that is all good. So that's 2 out of 2 correct on part B. And then lastly, for part C, the whole mess of this differential equation being separated and taking the integrals of. Again, the separation of variables, that's exactly what they're looking for. Running the integral on both sides, ending up with something like this, the negative 1 over y minus 2 with all of this on that right side is exactly what they're looking for. Solving for the constant of integration at the end there at c being equal to 1/3 is exactly what they're looking for as well. And then they run through making this look a lot nicer on this side, but this is still the same answer that they're looking for. They just kind of multiplied 6's on top and bottom. So that makes it negative 6 over x squared plus 2 on the bottom. But this matches exactly what we had at the start. They just made it cleaned up a little bit nicer. So that's exactly the form that they wanted in. So that's all 5 points here on this part being correct. So because I missed 2 on part A, that's 7 out of 9 for this page. Okay. You're older than me, yes, but yet we somehow graduated on the same year. So I don't know what you mean by you being my senior. We didn't go through high school together. We went to college together. We ended up exactly in the same classes. I don't know what you mean by senior in that sense. Okay, but that makes 7 out of 9 on that part. Okay. So with all of those, again, unfortunately, we dropped the ball a little bit in question number 6. I do a pretty good job on 5 and 6 for the most part, but we can go ahead and make our calculations here. So out of 54 points, out of all 6 problems, we end up with 2 lost and 4 lost. So that's exactly 50 out of 54 that we got correct at the end of the 2018 packet. So let's quickly take a look at what that will look like for ourselves on this part right here. Let me make sure we have everything set up here. So if we were to give this into a percentage here, that we had scored 50 out of 54 points, multiplying by 100 to make it a percentage, we end up with 92.59%. Okay. Something to note, of course, is that this AP exam is not graded out of 100. They only give you a score between 1 and 5, and it is curved based on the way that people score across the nation of that year. So with that will just about conclude. I think this is a pretty good score for now. Again, if we got that 52, I think that would have been a whole lot better. That was an easy problem at question number 6 that I should have gotten. So at 52, if it was 9 out of 9 on question number 6, that should have been a 96.29%. So a little bit of a mistake there towards the end with the slope fields, but it will be still something that we should be able to clear up the next time that we get back together on next week, Tuesday, for the next year's free response questions. So as always, everything will be going through our VOD system, the recording system on YouTube. This entire stream will be on there. And so we should have everything sorted out here in terms of this part of the live stream that we have together. So in any case, though, that will just about conclude it for today. I know that, I don't know if Nabil has his things that he's going over right now with Nicholas, but at least in terms of what I have here, that will just about do it for today. As always, all questions can be emailed to me directly at the labcoatmath@gmail.com, and we'll be continuing to upload throughout the week. I'm a little bit behind today, but there'll still be today's main video upload later tonight as well, once we finish this live stream. So again, as always, thank you everyone for coming in and supporting this channel. Of course, I think it's plenty of fun just going through these problems and making sure that everything is recorded in its own entirety, even though I myself am not exactly 100% perfect, but with our practice, I'm sure we will be able to hit 1 year in which we get all 54 correct, and you all will be there to see it. All right, so I think that will do it for just about today. You all can catch me again next week, Tuesday, from 4 to 7 p.m. Pacific time, and we'll see where that takes us. You all have a good one now, and we'll catch you on the next live stream.